Earthquake statistics. Alright. Let's take a deep breath, because earthquake statistics are one of those topics that sound simple until you actually start digging into them. Then you realize, wow, there's a lot going on beneath our feet, literally. I'm going to walk you through all of this in a very conversational, spoken way, almost like a long podcast monologue. We'll cover what earthquakes are, how they're measured, what the global numbers look like, how often big ones happen, what influences earthquake frequency, and what the stats actually mean for humans who live on this noisy, shifting planet. So, let's start from the beginning. 1. What exactly counts as an earthquake, statistically speaking? When scientists track earthquakes, they're not just counting the big dramatic ones you see on the news. They count every tiny tremor that shakes even the quietest corners of the earth. So, technically speaking, an earthquake is any sudden release of energy in the Earth's crust that creates seismic waves. Most of these releases are tiny, so tiny that humans don't feel them at all. If you stood on the Earth with some super sensitive equipment, you'd see that it's constantly buzzing. This is because tectonic plates are always moving, rubbing, colliding, separating, and sometimes breaking. The Earth's crust is not a smooth sphere. It's a cracked shell of plates that move like giant rafts on semi-molten rock. Now, here's where the statistics come in. When seismologists keep track of earthquakes, nearly all of their data comes from sensitive instruments, not from human observation. Humans can only feel earthquakes above a certain magnitude, usually something like magnitude 3.0 or so, depending on conditions. But seismic instruments pick up everything, even tiny ones as low as magnitude -2.0 that happen deep underground during fracking or mining or in very active tectonic areas. So right from the start, when we talk about how many earthquakes happen, you have to ask, what magnitude range are we talking about? Because the answer changes wildly depending on the threshold. 2. How are earthquake magnitudes measured? Let's talk about the magnitude scale real quick, because earthquake statistics don't make sense unless you understand what the numbers actually mean. Most people have heard of the Richter scale, but modern earthquake science has moved on to something called the moment magnitude scale, or MW. The important thing about this scale is that it's logarithmic. That means every whole number increase represents about 32 times more energy release. So a 7.0 isn't just a little stronger than a 6.0, it's releasing tens of times more energy. Here's why this matters statistically. There are huge numbers of small earthquakes because small energy releases are super common. But earthquakes get exponentially rarer as they get bigger. Think of it like raindrops. There are countless tiny droplets, fewer medium drops, and very few huge drenching bursts. Earthquakes behave the same way, except the energy difference between a tiny one and a huge one is mind-boggling. This exponential decline creates the backbone of earthquake statistics. 3. How many earthquakes happen globally per year? Now we get to the numbers, and they might surprise you. On average, Earth has somewhere on the order of approximately 500,000 detectable earthquakes per year. Approximately 100,000 earthquakes strong enough to be felt by humans. About 1,500 earthquakes per year that cause some kind of surface damage or real impact. So 500,000 earthquakes are happening every year, but only a fraction of them affect daily human life. Breaking this down by magnitude. Magnitude 2.0 to 2.9, hundreds of thousands per year. Magnitude 3.0 to 3.9, tens of thousands per year. Magnitude 4.0 to 4.9, a few thousand per year. Magnitude 5.0 to 5.9, about 1,000 per year. Magnitude 6.0 to 6.9, around 100 per year. Magnitude 7.0 to 7.9, roughly 10 to 20 per year. Magnitude 8.0 plus, about 1 per year. This drop-off is dramatic. If you plotted it on a graph, you'd see a steep downward slope, the Gutenberg-Richter frequency magnitude relation, which is the fancy scientific way of saying small quakes are common, big ones are rare. 4. Why do big earthquakes happen so much less often? The reason is simple. The Earth's crust can only accumulate large stress levels in limited regions along plate boundaries. Nature is constantly trying to release stress. Most of the time, little bits of the crust slip just a tiny bit, giving you those small quakes we don't feel. But sometimes stress builds up without release, over decades or centuries. When that happens, a major rupture zone forms, causing a large earthquake. This is kind of like bending a stick. If you bend it a little, it flexes back. But if you keep stressing it, eventually it snaps. The snapping is the earthquake. And the bigger the snap, the rarer it is. But the crust isn't uniformly stressed. Certain zones, like the Pacific Ring of Fire, are far more active because the tectonic plates there converge or slide past each other at higher rates. 5. Where do most earthquakes occur? Earthquake statistics become much clearer when you understand the geography of Earth's tectonic plates. About 90% of all earthquakes happen along plate boundaries, and 75% occur in the Pacific Ring of Fire. Some of the most active zones: Japan and the Western Pacific, Indonesia, Chile and the western coast of South America, California and the San Andreas Fault, Alaska and the Aleutian Trench, Turkey and the Anatolian Fault, New Zealand's Alpine Fault. These places have subduction zones, where one plate sinks beneath another, and transform boundaries, where plates slide horizontally past each other. Both of these boundary types are extremely prone to earthquakes. There are also intraplate earthquakes, earthquakes that happen in the middle of continents, far from plate boundaries, like in the central United States or India. They're quite rare statistically but can be very damaging because they're often shallower and occur under regions not built for seismic activity. 6. How predictable are earthquake statistics? Earthquake numbers are statistically predictable but not individually predictable. This is an extremely important distinction. What we can predict: we can estimate how many earthquakes of each magnitude will occur on average per decade or per century. The Gutenberg-Richter law, which I mentioned earlier, helps predict the probability of earthquakes based on magnitude. That's why we can confidently say there will probably be about a dozen magnitude 7 earthquakes each year. There will likely be one magnitude 8 somewhere on Earth each year. Magnitude 9 earthquakes, like the 2011 Japan quake, might occur once every 10 to 30 years globally. What we cannot predict: we cannot say a magnitude 8 will strike Tokyo next Thursday at 3 p.m. Science has not figured out short-term earthquake prediction, and most scientists doubt it's even possible in the way we imagine. Earthquakes are extremely chaotic, governed by complex physics happening miles below the surface. But probability-wise, yes, probability is our friend here. 7. Long-term earthquake frequency patterns. Earthquake occurrence tends to follow long-term statistical trends. Over decades, the number of earthquakes above a certain magnitude stays surprisingly consistent. But the key is, earthquake activity fluctuates over short timescales. Some years you might get more magnitude 7 earthquakes than average, fewer magnitude 6 earthquakes, several aftershocks that skew the numbers. For example, after major earthquakes, aftershock sequences can include hundreds of smaller quakes, temporarily boosting the annual count. But we don't consider this an increase in tectonic activity overall, it's just part of the natural event cycle. Like how one stormy week doesn't prove the climate is permanently stormier. 8. What about earthquake swarms? An interesting statistical phenomenon is earthquake swarms, clusters of many small earthquakes without a major one. Volcanic regions, in particular, experience swarms. Examples: Yellowstone, Iceland, Japan. Northern California. Swarms might include dozens, hundreds, or even thousands of tiny earthquakes over days or weeks. Statistically, these can skew local numbers upward. But globally, they don't significantly change the year's earthquake totals because the Earth is so large and already so active. Swarms are statistically fascinating because they challenge the typical idea of a main shock aftershock pattern. In swarms, it's unclear which quake, if any, is the main event. They're almost like Earth's jittery nervous tics rather than major muscle contractions. 9. How deadly are earthquakes statistically? Now let's talk about human impact, which is where earthquake statistics really matter for society. A small earthquake in a dangerous location can be far deadlier than a large earthquake in a remote or prepared region. For example, a magnitude 6.0 in an unprepared, densely packed region can kill thousands. A magnitude 7.5 in the middle of the ocean might kill no one. Human vulnerability is the real variable. Death tolls usually depend on population density, quality of buildings, depth of the earthquake, time of day, whether secondary disasters occur, tsunamis, landslides, fires. Statistically, the deadliest earthquakes in history often weren't the largest magnitude-wise, they were the ones that struck fragile societies. The 2010 Haiti earthquake, for example, was only magnitude 7.0 but killed hundreds of thousands due to poor building infrastructure. Compare that with Japan, where a magnitude 9.0 caused extensive damage but far fewer deaths relative to the enormous power involved, although the resulting tsunami was horrific. So the human impact statistics show something profound. Earthquake danger is as much sociological as geological. 10. Long-term global earthquake deaths. If you look at earthquake fatality statistics across the decades, there's a downward trend in many parts of the world thanks to better building codes, early warning systems, global communication, rapid emergency response. But in poorer regions, earthquakes still cause major disasters. Statistically, a single catastrophic earthquake can dominate an entire decade's death toll. One thing that complicates earthquake fatality statistics is the fact that very large earthquakes, like magnitude 8 or 9 events, are relatively infrequent but extremely lethal when they hit populated coasts. And when they generate tsunamis, casualties multiply dramatically. So statistically, earthquake deaths are heavy-tailed, meaning a few extreme events contribute the majority of total fatalities. 11. Are earthquakes increasing? This is a common question. Statistically speaking, no. Earthquakes are not increasing globally. The total number of earthquakes has remained relatively consistent over the long term. But there are 3 reasons why people think earthquakes are becoming more frequent. News coverage and social media amplify awareness. More seismic instruments exist today, detecting smaller quakes that used to go unnoticed. More people are living in quake-prone regions, making the impacts seem more frequent. So, the perception has changed, but the underlying statistics show no meaningful increase in global tectonic activity. 12. What about human-caused earthquakes? Another modern statistical wrinkle is induced seismicity, earthquakes caused by human activities. These include wastewater injection from oil and gas drilling, hydraulic fracturing, fracking, reservoir filling behind large dams, underground mining, geothermal energy extraction. These induced earthquakes can increase the number of small to moderate earthquakes in certain regions. The U.S. Midwest, for example, has experienced spikes in earthquake counts linked to injection wells. But globally, induced earthquakes are still a very small percentage of total seismic activity. They do, however, affect local earthquake statistics dramatically in certain areas. 13. Earthquake depth statistics. Depth plays a huge role in earthquake characteristics. Earthquakes can occur anywhere from the surface down to about 700 kilometers in subduction zones. We classify them as shallow, O-70 kilometers deep; intermediate, 7O-300 kilometers deep; 3O-700 kilometers. Statistically, shallow earthquakes make up the majority and cause most damage because they occur near the surface. Deep earthquakes are less common but can be very powerful, though usually less damaging. Subduction zones are responsible for the deepest earthquakes, often hundreds of kilometers below the surface where a sinking plate bends and compresses. 14. The largest earthquakes in history, statistically significant events. If we look at the most powerful earthquakes ever recorded, they are almost all associated with major subduction zones. 1960 Chile, MW 9.5. 1964 Alaska, MW 9.2. 2004 Sumatra, MW 9.1-9.3. 2011 Japan, MW 9.0. Magnitude 9.0 plus events are extremely rare, maybe once every 20 to 40 years. They release incredible energy. Even though they're only one magnitude unit above an 8.0, they release over 30 times more energy. Statistically, these quakes dominate seismic energy release charts. 15. Summary of major statistical points. To wrap this up before giving you a concluding, spoken flourish, here are the core statistical takeaways. Earth has roughly 500,000 earthquakes per year, most too small to feel. Earthquake frequency follows a logarithmic pattern. Small quakes are common, big ones rare. Only about 1 magnitude 8 earthquake occurs globally each year. Magnitude 9 earthquakes are extremely rare. Most earthquakes occur along tectonic plate boundaries. Earthquakes are not increasing globally, but detection and reporting are. Human impact depends heavily on social factors like building codes. The deadliest earthquakes aren't necessarily the strongest. Earthquake fatalities are statistically dominated by a small number of catastrophic events. 16. A closing spoken style reflection. So, if we step back and think about what all these numbers are telling us, it's actually kind of beautiful in a strange, tectonic way. The earth is constantly shifting, like a living thing that breathes in slow motion. Most of these movements are tiny little whispers we never hear. But every so often, the earth speaks loudly. And when it does, the entire planet listens. The statistics tell us something profound. Earthquakes are both completely predictable and totally unpredictable. Predictable in the sense that we know how many to expect each year, and we know where most of them will occur. But unpredictable in that no one can tell us exactly when or where the next big one will strike. It's a reminder that human civilization, for all its skyscrapers and satellites, still depends on a fragile crust floating on molten rock. The numbers show us patterns, rhythms, probabilities, but they don't give us certainty. And maybe that's a good thing. Maybe it keeps us humble. At the end of the day, earthquake statistics help engineers build safer buildings, help governments prepare for disasters, and help scientists understand the deep workings of our planet. They're not just numbers, they're a kind of language the Earth uses, a language we've only recently learned to interpret. And that, in a nutshell, is your long, spoken explanation of earthquake statistics. The impact of earthquakes. Imagine for a moment that you are standing on solid ground, your street, your kitchen floor, a field, anywhere. It feels stable. It feels permanent. Yet beneath that ground, our planet is constantly moving, slowly shifting huge slabs of rock called tectonic plates. Most of the time we never notice it. But sometimes, those plates lock, pressure builds, and suddenly the earth releases that energy in a violent jolt. That jolt is what we experience as an earthquake. Today, I want to walk you through the impacts of earthquakes in a way that feels like a spoken lecture or a talk, something smooth, flowing, and comprehensive. We'll look at earthquakes not just as geological events, but as forces that shape societies, economies, cultures, and even psychology. We'll move through physical effects, human effects, economic consequences, environmental change, long-term recovery, and what earthquakes teach us about resilience and planning. 1. The physical impact. What actually happens when the ground moves? Let's begin with the most immediate, intuitive impact, physical shaking. An earthquake's shaking can vary from gentle rocking to the kind of violent motion that tosses cars around, collapses buildings, and rips open the ground. The severity depends on factors like magnitude, depth, distance from the epicenter, and type of soil. During strong shaking, buildings endure stresses they may not be designed for. Structures sway, walls crack, windows shatter, and in the worst case scenarios, entire buildings collapse. This collapse is often the leading cause of injury and death in earthquakes. It's not the earthquake that kills people directly, it's the built environment failing under stress. In regions with soft, loose soil, something called liquefaction can occur. Imagine soil suddenly behaving like a liquid, solid ground loses its strength, and buildings tilt or sink. A stable street can buckle like cardboard. This effect can utterly transform a city block in seconds. Earthquakes can also trigger ground rupture, where the earth literally tears open along a fault line. Highways split, pipelines snap, and railway lines become distorted. This can render entire transport networks unusable until repairs are made. Then there are landslides, which are extremely dangerous, especially in mountainous or hilly regions. A violent earthquake can loosen huge masses of rock and soil, causing them to slide downslope with tremendous speed. Entire villages have been buried in such events. Landslides can block roads, rivers, and valleys, creating secondary floods or isolating communities for days or weeks. Finally, earthquakes that occur under the ocean or near coastal regions can trigger tsunamis. These enormous waves travel at high speeds across oceans and crash into coastlines minutes or hours after the initial quake. Tsunamis amplify the destructive power of earthquakes far beyond the epicenter, sometimes affecting countries thousands of miles away. So the physical impact is multifaceted: shaking, liquefaction, ground rupture, landslides, tsunamis. All of these create immediate danger and set the stage for the human and economic impacts that follow. 2. Human impact, loss, survival, and the struggle in the aftermath. When we talk about the impact of earthquakes, the human dimension is the most heartbreaking and compelling. Earthquakes can strike with no warning, giving people only seconds to react. That suddenness often leads to panic, confusion, and trauma. The immediate human impacts include injury, death, and psychological shock. People may be trapped under rubble, disoriented, or searching for their loved ones. Emergency response teams, often from the local community at first, begin searching through debris, sometimes with nothing but their hands. In addition to physical injuries, earthquakes lead to emotional trauma. Survivors may live with anxiety, nightmares, or long-term post-traumatic stress. The sense of security that comes from feeling the ground is stable, something we usually take for granted, can be deeply shaken, leaving people uneasy for years. Homelessness is another major consequence. Homes can become uninhabitable even if they remain standing, because their structural integrity might be compromised. Thousands or even millions of people can be displaced in a large quake, seeking shelter in tents, cars, or emergency centers. Then there's the disruption of essential services. Electricity goes out. Water lines break. Gas pipes can rupture, leading to fires. Cell networks crash just when people most desperately need to communicate. Hospitals become overwhelmed, sometimes even damaged themselves, making care difficult when it's most needed. Schools close. Workplaces shut down. Families may be separated. Children may lose access to normal routines and stability, which is critical for emotional health. In the days and weeks after a major earthquake, the priorities for survival include finding food, water, and shelter. Relief organizations and governments mobilize, but the scale of the need can overwhelm even well prepared systems. Aftershocks add to the fear, sometimes causing further damage and preventing rescue and rebuilding efforts from proceeding safely. So the human impact is not just about the moment of shaking, it's about the entire arc of survival, coping, healing, and rebuilding. 3. Economic impact. Rebuilding after destruction. Earthquakes have enormous economic consequences. In major city center earthquakes, where dense populations and infrastructure concentrate, the price tag of recovery can reach billions or even hundreds of billions of dollars. Let's break down where these costs come from. 1. Rebuilding infrastructure. Roads, bridges, power lines, water systems, sewer systems, subway systems, all of these can be severely damaged. Restoring them is a massive undertaking involving specialized equipment, skilled workers, and time. 2. Damage to buildings. Homes, office towers, factories, schools, hospitals, every category of building can suffer damage. Insurance may cover some losses, but uninsured communities face long delays and hardships. 3. Business disruption. When offices and factories shut down, businesses lose income. Workers lose wages. Supply chains falter. Shops may be unable to reopen for days or weeks. Even businesses that remain physically untouched can suffer if their customers or suppliers are affected. 4. Agriculture and natural resources. Landslides can destroy farmland. Irrigation systems may break. Livestock can die or escape. Fish farms and coastal industries can be wiped out by tsunamis. 5. Long-term recovery costs. Rebuilding isn't just about replacing what was lost. It's about redesigning infrastructure to be safer, stronger, and more resilient. That often means upgrading building codes, retrofitting structures, and training construction workers in earthquake-resistant techniques. Economically, earthquakes hit developing countries hardest. Wealthier nations usually have better building codes, stronger infrastructure, and more resources for recovery. Poorer nations often lack these advantages, leading to disproportionate human and economic losses. 4. Social and cultural impact. Communities, traditions, and social fabric. Beyond physical destruction, earthquakes affect the social structure of communities. In some places, earthquakes can weaken trust in government if response efforts are slow, uncoordinated, or unequal. Conversely, strong disaster response can build trust and unity. Earthquakes also disrupt cultural life. Places of worship, historic buildings, museums, and cultural landmarks can collapse or suffer severe damage. These structures often carry deep emotional and historical significance for communities. Their loss can feel like a wound to cultural identity. Communities may be relocated entirely. People who have lived in the same village for generations may suddenly be forced to move to new housing developments or distant cities. The cultural traditions tied to specific places, local festivals, architecture, rituals, may fade or change. In devastating earthquakes, the diaspora effect occurs. People leave the affected region permanently. This migration can shift demographics, labor patterns, and family structures. On the other hand, earthquakes can also bring communities together. People often help one another in extraordinary ways, providing food, shelter, or comfort. Shared hardship can strengthen bonds among neighbors who may have barely known each other before. 5. Environmental impact. Changing the landscape. Earthquakes reshape the natural environment in profound ways. Some impacts are destructive, others create new landscapes. 1. Shape of the land. Earthquakes can raise or lower sections of land by several meters. In some cases, entire coastlines rise, exposing reefs and expanding beaches. In other cases, land subsides, permanently flooding areas. 2. Rivers and water flow. Landslides can block rivers, creating natural dams. These dams can later burst, causing flash floods. In contrast, ground uplift can divert rivers entirely, creating new channels. 3. Soil quality. Liquefaction can ruin agricultural soil, reducing fertility. But in some cases, new sediment deposits can enrich the land. 4. Ecosystems. Forests can be flattened. Lakes can drain or form. Wildlife habitats can disappear or emerge. Species may migrate or decline. 5. Fires and pollution. Gas line ruptures can ignite fires. Industrial facilities damaged in earthquakes can release chemicals, causing environmental contamination. Tsunamis can drag debris, sewage, and hazardous materials far inland. The environmental impact reminds us that earthquakes are not just human events, they are planetary forces. 6. Long-term recovery. Rebuilding lives and cities. The recovery phase after an earthquake can last years or even decades. It involves more than rebuilding structures. It's about restoring normal life, and often about improving on what existed before. Reconstruction is usually divided into phases: emergency response, temporary shelter, long-term housing, infrastructure rebuilding, and economic revitalization. Each phase requires planning, funding, and community involvement. Authorities often must decide whether to rebuild in the same location or relocate communities to safer areas. These decisions can be controversial, balancing safety with cultural heritage and personal attachment. Improving building codes becomes essential. Many cities around the world adopt stricter construction standards after major earthquakes. Retrofitting older buildings is expensive but can save lives in future quakes. Education also plays a role. Earthquake drills, evacuation plans, and public awareness campaigns help prepare people for the next event. Countries like Japan and Chile are examples of nations that have invested heavily in earthquake preparedness, reducing casualties significantly even in very strong quakes. For individuals, recovery may mean psychological therapy, rebuilding homes, finding new jobs, or re-establishing routines. Children may need support returning to school. Businesses may need loans or subsidies to reopen. Governments and NGOs help, but the process is slow and emotionally heavy. 7. Lessons learned, resilience, preparedness, and the future. Earthquakes teach us important lessons about resilience. They remind us that the ground beneath us is not as stable as it feels, and that human societies must adapt to natural forces. One lesson is the importance of scientific monitoring. Seismologists use networks of instruments to detect ground movement, understand fault lines, and model potential scenarios. While predicting the exact moment of an earthquake remains impossible, scientists can identify high-risk areas and help governments plan accordingly. Another lesson is public education. People who know what to do during an earthquake, drop, cover, and hold on, are far more likely to stay safe. Communities with evacuation plans for tsunamis reduce casualties dramatically. And perhaps the biggest lesson is the value of building resilience before disaster strikes. Strong building codes, emergency supplies, community coordination, and early warning systems can mean the difference between a tragic catastrophe and a manageable event. Resilience also applies socially. Communities that foster mutual support networks recover faster. Societies that invest in mental health resources help people heal better. Governments that communicate transparently maintain public trust. 8. Earthquakes as part of Earth's story. Finally, we can place earthquakes in a broader perspective. They are part of the dynamic nature of our planet. Earthquakes shape mountains, create valleys, and influence the course of rivers. Without tectonic activity, Earth would not have continents, oceans, or diverse landscapes. So while earthquakes can cause immense suffering, they also remind us that we live on a living, breathing planet, one that evolves over time. Understanding and respecting that dynamic can help us live more safely and sustainably. Omori's Law. Let me take you on a long, clear, and fully spoken journey into one of the most important ideas in earthquake science, something researchers rely on every day when they try to understand how the earth settles after a major rupture. This idea is called Omori's law, named after the Japanese seismologist Fusakichi Omori, who lived in the late 19th and early 20th centuries and made an extraordinary contribution to our understanding of how the ground behaves after it has been violently disturbed. When a major earthquake strikes, we often imagine the shaking, the collapse of structures, the loud rumbling, and the single moment of catastrophic release. But an earthquake is rarely just one event. It is more like the beginning of a long sequence of tremors, small and large, that can continue for days, weeks, months, or even years. The ground does not simply rupture and then fall silent. Instead, it behaves like something that has been hit too hard. It vibrates, it settles, it shifts, it adjusts, and it tries to find a new equilibrium. All of those post-main shock tremors are called aftershocks. Now, the key question scientists began asking as they mapped earthquake sequences was this: is there any pattern to how aftershocks occur? Do they come completely at random? Or do they follow some kind of natural rhythm or rule? This is where Omori's law changes everything. Long before sophisticated computing, vast seismic networks, satellite systems, or high-speed modeling methods existed, Omori painstakingly collected observations of earthquakes and the smaller tremors that followed them. Through careful study, he noticed something striking. Aftershocks become less frequent as time passes, and they do so in a very particular way. To put it simply, right after a major earthquake, aftershocks occur very frequently. As time continues, the frequency gradually decreases. The decline in that frequency follows a smooth, predictable pattern. That pattern is what we now call Omori's law. The idea behind the law. To really grasp what the law means, imagine the Earth's crust as a complex system of blocks and fractures. When a large fault suddenly slips, enormous forces that were locked inside the rock are abruptly released. But not all of the stress is released in that one instant. Some stress is redistributed to nearby parts of the crust. Those zones of redistributed stress take time to settle, and as they do, they produce aftershocks. Omori's law provides a way of describing how quickly the settling process slows down. Instead of giving the familiar mathematical formula with symbols, since you've asked for no Greek letters and no numerical symbols, let me explain the law in plain language. Omori's law says that the rate at which aftershocks occur decreases over time in a way that starts out very steep and gradually levels out. Immediately after the main shock, the ground is extremely unstable, so aftershocks happen rapidly. But as minutes become hours, hours become days, and days stretch into weeks, the earth slowly settles, and the aftershocks become less frequent. Now, what makes Omori's law so remarkable is that it does not just say the rate decreases, it says how it decreases, and it implies a shape to that decrease. The drop in aftershock rate is not abrupt. It is not jagged. It follows a specific type of curve that declines quickly at first and then more slowly later on. This curve captures a universal behavior seen across countless earthquake sequences around the world. The conceptual form of the law. To give you the conceptual version, imagine drawing a graph, again, no numbers, just the shape. Along the horizontal axis, you have time since the main shock. Along the vertical axis, you have the frequency of aftershocks at that moment. If you look right next to the beginning, the time right after the main shock, the curve is high because the aftershock rate is high. Then the curve bends downward sharply, showing the rapid, early decline. As you move farther along in time, the curve still slopes downward, but more gently. It never truly hits zero. Instead, it stretches out farther and farther, getting ever closer to silence but continuing to produce occasional tremors long after the main shock. This behavior aligns with the way strains and stresses relax inside rock masses. After a major rupture, the surrounding rock does not all adjust at the same pace. Some patches release stress quickly, others take longer. Some fractures triggered by the main shock slip right away, others remain poised until a small stimulus nudges them. The Earth, in this sense, is full of delayed reactions. Omori's law captures that entire orchestra of delayed responses in a single beautifully simple idea. The farther you are from the moment of the main shock, the fewer aftershocks you get, and the rate declines in a smooth and predictable way. Why the law matters? It might sound like just a descriptive statement: aftershocks get less frequent with time. But Omori's law is much deeper than that. It is a cornerstone of seismic hazard planning, emergency response, and scientific understanding for several reasons. First, it helps predict the likelihood of aftershocks in the immediate hours following a major quake. Emergency responders need to know whether another significant jolt may strike soon after they move into damaged zones. Second, it helps engineers and city planners understand how long the ground may remain unstable. This is critical for examining compromised buildings and infrastructure that might fail under further shaking. Third, it serves as a fundamental benchmark for earthquake physicists developing models of stress transfer and crustal relaxation. If a model does not reproduce the Omori pattern, it is likely missing something important about real-world fault behavior. The original versus the modified form. Omori originally described the law in a relatively simple form. Later, scientists found that in many real earthquake sequences, a slightly more flexible version gives a better fit. This is now known as the modified Omori law. Since we are not using letters or numbers, let me explain the difference completely in words. The original version basically said, the aftershock rate decreases in inverse proportion to the passage of time since the main shock. The key phrase here is inverse proportion. What this means is, as time increases, the rate decreases, and the decrease follows a curve shaped by the reciprocal of time. The modified version adds one more idea. Right after the main shock, time cannot be treated as zero. There is always a very short span during which the first measurable aftershocks begin. To account for this, the modified form shifts the entire curve slightly so that the earliest moment is not truly zero. In normal mathematical writing, this would involve adding a term that represents a very small initial offset. But since we are avoiding symbols, all you need to know is that the modified version starts the clock a tiny bit after the true main shock time so the curve behaves realistically. What the law does not say. Before digging deeper, it's just as important to understand what Omori's law does not claim. It does not say anything about the size of aftershocks. It deals only with frequency, how often they occur, not how strong they are. It does not predict the occurrence of a specific aftershock at a specific moment. It describes an overall pattern, not an exact schedule. It does not imply that aftershocks will vanish at a predictable time. The decline gets very slow as time goes on, and some aftershocks may happen long after the main shock. It does not require the Earth to behave perfectly the same everywhere. It describes a pattern that emerges on average, over many aftershocks, not a strict law of nature that every individual sequence must obey exactly. Why the pattern happens, what causes this particular shape, this rapid then slow decline, is a fascinating question. Several explanations have been proposed, and they fall generally into two families. One family blames stress relaxation. When a major fault ruptures, it redistributes stress throughout the surrounding crust. Some parts become more stressed and are more likely to slip. Others become less stressed. The parts that were primed to slip do so soon after the main shock, generating rapid, early aftershocks. The remaining potential sites slip more slowly, generating later ones. Another family focuses on frictional healing. Rock surfaces in fault zones are not smooth. They are rough, broken, granular, and often full of crushed material. After a slip event, These surfaces begin to lock together again, increasing resistance to further motion. The locking process is fast at first and then slower over time, matching the decline in aftershock rate. A third family looks at fluid pressure. Deep underground, water and other fluids can move through cracks created by the main shock. As pressure diffuses through these openings, it affects the likelihood of additional slips. This diffusion follows a pattern that naturally produces a decline resembling Omori's law. Different earthquakes may involve different combinations of these mechanisms. But regardless of the cause, the same kind of time-decreasing curve emerges again and again. Observational strength of the law. One of the reasons Omori's law is so respected is its empirical power. It has been tested on earthquake sequences from volcanic zones, subduction zones, continental faults, induced seismicity regions, and more. Nearly everywhere scientists examine the aftershocks of a significant main shock, the pattern appears. The exact steepness of the decline may vary depending on local conditions, fault complexity, fluid pressures, crustal composition, and other factors, but the overall behavior remains robust. This universality is astonishing when you think about how chaotic the Earth's crust is. It is tangled, fractured, irregular, layered, intersected by faults of all scales, and influenced by heat, water, pressure, and tectonic forces. Yet in the midst of all this apparent randomness, aftershocks around the world follow a remarkably similar time decay trend. This is one of the great beauties of seismology. Amid extraordinary complexity, simple patterns emerge. A deeper look at the curve. Because we are not using numerical symbols or mathematical expressions, I will describe the curve in intuitive spoken terms. Imagine standing beside a quiet lake. You pick up a stone and throw it into the water. At first, ripples appear rapidly, one after another, moving fast and with high energy. As time passes, the ripples grow broader and slower. Eventually, they fade into a calm surface. Aftershocks follow a similar rhythm. The Earth's crust has been struck with immense force, not by a stone, but by the release of long-stored tectonic stress. This generates seismic waves that affect the surrounding rock. The aftershocks are like the ripples. They come quickly at first, then slower still. But unlike ripples, which fade completely, the aftershock sequence persists for much longer. And instead of a smooth circular pattern across a lake, the aftershock zone reflects the shape of the fault, the local geology, and the stress field. Still, the time decay behavior, that steady slowing, remains unmistakable. Relation to seismic hazard. Emergency management agencies pay close attention to Omori's law during crisis response. Why? Because they need to make decisions about when to send rescue teams into collapsed structures, how long to keep certain zones evacuated, how to allocate medical, logistical, and engineering resources, whether the risk of additional damaging shocks is rising or falling, how to schedule recovery operations. Because the earliest period after a large earthquake tends to have the highest chance of a strong aftershock, emergency crews often proceed cautiously in that window. As time passes and the rate drops, they can operate with increasing confidence. Omori's law gives them a scientific basis for this timing. It is not perfect, no seismic prediction law is perfect, but it offers a reliable statistical framework that complements other tools like stress transfer modeling, ground deformation tracking, and empirical analysis of fault behavior. The law across scales. Another remarkable thing is that Omori's law applies across a wide range of earthquake sizes. Whether the main shock is relatively small or devastatingly large, the aftershocks tend to follow the same kind of decline in frequency. Larger main shocks produce more aftershocks, but the overall pattern still resembles the Omori curve. Smaller ones produce fewer, but again the rate decrease fits the familiar shape. This scalability suggests that the physics of aftershock generation may have universal components, deep rules governing how faults relax and how stresses propagate. criticisms, refinements, and open questions. Science is always evolving, and Omori's law has been refined repeatedly over more than a century. While the overall idea remains robust, researchers continue to debate issues such as: does the rate always follow the same steepness in different tectonic environments? In some volcanic or geothermal regions, aftershocks may behave differently due to the influence of heat and fluids. How does the presence of complex networks of faults affect the decay of aftershocks? Some zones have so many intersecting fractures that the sequence can be unusually complicated. Can we separate triggered events from natural background seismicity? Sometimes aftershocks blend into ongoing natural activity, making it hard to identify what belongs to the sequence. How do deep and shallow earthquakes differ in their aftershock decay behavior? The pressure, temperature, and rock properties at depth may change how the sequence evolves. Is Omori's law fundamental, or does it emerge from deeper physical processes that we do not fully understand? Some researchers believe it arises from frictional physics, others believe it emerges from stress diffusion, others think it may relate to universal statistical behaviors found in complex systems. These questions show that Omori's law is not the final answer but rather a starting point, a clue pointing toward deeper mechanisms that scientists continue to investigate. Examples without numbers. Let me describe hypothetical examples without any specific numerical values. Imagine a major earthquake beneath a mountain range. In the moments immediately following this quake, the ground trembles repeatedly as small nearby fractures slip. Within a short time, the frequency of these tremors is extremely high, not enough time passes between them to let emergency crews feel safe. As hours go by, the bursts of motion grow less frequent. The rate at which the ground shakes begins to slow. Rescue crews still hear and feel tremors, but they come with longer pauses between them. As days pass, the pattern continues. The tremors remain but are spaced farther apart. Scientists monitoring the sequence see the familiar curve: rapid early decay, followed by a slower decline. Weeks later, aftershocks still occur but are now occasional. Months later, a lone tremor may strike unexpectedly, a reminder that the crust is still adjusting, but the intensity of the sequence has mostly faded. This qualitative story, though it uses no specific numbers, is the essence of Omori's law in practice. The human side of the law. One of the lesser discussed aspects of Omori's law is the psychological effect it has on communities recovering from an earthquake. After a major quake, residents are often terrified of aftershocks, especially because one of them might be large enough to cause additional damage. The steady decline in aftershocks, which the law predicts, becomes a kind of emotional reassurance. People begin to sleep more easily once the ground stops shaking several times a day. They return to their homes, resume daily routines, and feel a sense of control returning. Even though Omori's law is essentially a statistical pattern, it intersects powerfully with the lived experience of earthquake survivors. Omori himself. It is worth pausing to appreciate that this law is named after a person who did not have access to modern seismic networks or rapid computing. Fusakichi Omori worked with painstaking observations, early instruments, and manual records. His insight came not from high-powered models but from careful, patient study. He noticed a pattern where others saw only chaotic sequences of tremors. His observational genius allowed him to articulate a rule that still underpins seismology today. Why Omori's law survives in modern times. Even with the advent of advanced physical models, incorporating friction laws, stress redistribution, crustal heterogeneity, and fluid dynamics, Omori's law remains relevant because it captures something fundamental. Many elaborate models, when simplified or examined at large scales, naturally reproduce Omori-type decay. This suggests that the law reflects a deep property of how faults behave under stress. It also continues to be used because it is practical. Emergency management agencies cannot wait for sophisticated computer simulations to run during a crisis. They need immediate estimates, and Omori's law provides a quick approximation of aftershock hazard. The spoken summary. If I were to summarize Omori's law in the simplest spoken sentence possible, without mathematical symbols, it would be: after a major earthquake, aftershocks occur frequently at first, then gradually become less common, following a smooth decline that slows over time. That is the heart of it. A closing reflection. Omori's law is much more than an equation. It is a window into how the earth relaxes after violent strain. It shows that even the seemingly chaotic sequence of aftershocks contains order, rhythm, and predictability. It bridges the worlds of observation and theory, linking human experience, the fear of ongoing shaking, with deep geophysical processes unfolding far beneath our feet. In many ways, the law reminds us that the Earth, like any stressed system, takes time to heal. It does not snap back into place instantly. It trembles, adjusts, and slowly calms itself, and humanity has learned to read those signs. That is the essence of Omori's law. A long, graceful, worldwide pattern in the Earth's